Ever wonder how a robot could understand the physics of a swinging pendulum or a bouncing spring? What if I told you AI is getting closer to grasping the universe's hidden rules, not just guessing outcomes, but comprehending the math that shapes reality? Let's dive into a breakthrough that's changing how machines learn the language of physics. So here's the big idea. Scientists are teaching AI to model energy, the invisible force that drives everything from planetary orbits to chemical reactions. Think of energy as the universe's blueprint. It's split into two parts: kinetic energy, the energy of motion, and potential energy, stored energy, like a stretched spring or a ball high in the air. By breaking energy into these pieces, AI can simulate how systems evolve over time. Imagine a neural network as a flexible math tool. It doesn't just memorize data, it learns patterns, like how a pendulum swing follows a specific rhythm. But here's the twist: these models adapt dynamically. For example, they adjust friction or energy loss in real time, like a damped oscillator slowly losing speed. This is done using clever techniques, like a hypernetwork that generates parameters on the fly, letting the AI tweak its predictions as conditions change. To test this, researchers built a library of classic physics problems. 1. Mass spring systems, like a bouncy object on a spring. 2. Pendulums, swinging clocks. 3. Duffing oscillators, chaotic, hard-to-predict systems. 4. Dissipative systems, like gas containers exchanging heat. They used numerical methods to simulate these systems, creating vast datasets of motion. Then they trained AI to predict these trajectories, without just copying the data, but understanding the underlying physics. The stars of the show. Two methods, RO and Mr. These AI models use meta-learning, a way of teaching machines to learn how to learn. Think of it like training a robot to solve puzzles by showing it different types of puzzles. The result? RO and Mr. outperformed traditional methods, especially when given more data. For example, with a mass spring system, RO and Mr. improved dramatically as they saw more examples. In chaotic Duffing oscillators, they avoided cheating by memorizing data, instead learning the system's true rules. Even in energy loss scenarios like a pendulum with friction, Mr. nailed the predictions, staying accurate over time. Here's what makes these models revolutionary: they don't just guess outcomes. They encode physical constraints directly into their architecture. For instance, a Hamiltonian neural network ensures energy is conserved by mathematically enforcing the system's total energy as a constant. Meanwhile, port-Hamiltonian models extend this to systems with external forces, like friction or heat exchange, by introducing ports that represent energy flow. But here's the kicker: traditional models require explicit knowledge of all parameters up front, like a pendulum's mass or a fluid's viscosity. If those change, you'd have to retrain the model from scratch. This is where modulation-based frameworks shine. Think of them as a universal remote for physics: one base model, plus a tiny code that tweaks its behavior for new scenarios. Instead of hard-coding every variable, the model learns to guess the right parameters from a simplified, low-dimensional code. Let's unpack how this works. For energy-conserving systems, like a frictionless pendulum, the model uses a neural network to encode the system's energy blueprint. This network outputs a function that maps states, position, velocity to energy values. For systems with friction or heat loss, it adds another layer to account for entropy, essentially, a second neural network that models energy dissipation. By modulating these networks with latent variables, the model can simulate entirely new configurations without starting over. The results? In tests, this approach outperformed traditional methods in few-shot learning, predicting accurate dynamics with just a handful of examples. Whether it's a pendulum with a different mass or a fluid with new viscosity, the model adapts seamlessly. And crucially, it maintains the essential physical constraints that keep simulations stable. So what's the big deal? This isn't just about faster simulations. It's about building AI that understands the rules of the universe, not just memorizing patterns. From climate modeling to robotics, this could revolutionize how we design systems that interact with the physical world. Thanks for watching. If you want to explore how these models work in action, check the links below. And don't forget to like, subscribe, and hit that bell for more deep dives into the science shaping our world. See you next time. Remember, the next time you see a pendulum or a planet in motion, scientists are working to teach machines not just what to predict, but how to respect the laws that make the world tick. And that's the future of scientific machine learning.